So Regev commented that he thought it was time to clean up how the breadboards looked, and I think he had a good point. This is how it looks now. I did clean it up quite a bit, and the main difference right now, the memory unit used to be made up of the memory unit itself, the RAM here, and the memory programmer. But now the programmer is separate, equipped with our transceivers, so I could plug this in whenever we need, right to the memory. And right now it's connected to the instruction memory address register. It's able to actually pull the memory to pull up whatever is at that byte of data, which in this case would be instructions. Right now we don't have any instruction decoding going on, so it's just going to sit there, but that's how it works now. So the CPU can just go up with its instruction pointer and then execute that code. To make this work, we do need to have some data on the RAM itself. There's going to be garbage data at pretty much every address. So I think what we should do is plug this in, and then we can write whatever bytes we want to the next couple of addresses, so that as we increment, we can see that the addresses that we write in with our programmer can be read independently by the IMAR. They're able to work together because of these 245s that we have here, these bus transceivers. So right now these are turned off, meaning that the RAM can be accessed by anybody else without any kind of contention. And then all of our input here is also gated pretty much by these 245s. So we have a very logical approach here where we can turn on or turn off the input, and the RAM doesn't need to listen to a bunch of people at once, which could create problems for us. The output enable is pulled up over here, so these chips are disabled, meaning the IMAR is not able to talk to the RAM, and it's ready for us to talk to it with our programmer. So I'm going to plug in the 16 bits of address lines, which only 15 are going to be used, but I still use the 16 bits. And we have our 8 bits of data, so we're going to pretend that we're putting in a bootloader. We're putting that initial data on the RAM that needs to execute for the CPU to start, but in the future this will all be automated. So let's plug this in and try and get that going. So these are going to go into these address lines, and it has to be on the far side because right now it's going to take input here, and on this other side is directly connected to the RAM. So we're not really skipping the logic, but this guy sort of belongs to the IMAR, and my output already has that logic built in. So I can go directly into the RAM here and still maintain control from the actual programmer side itself. So I'm going to put these in order. Okay, so there are our address lines, and now we need our data be a lot faster. So these should be able to just go right in. All right, let's plug in our power, and let's power up the RAM itself, because right now it's not powered up. So now our controller is plugged in, and I'm going to do a simple sample data test, and it does turn on. You can see down here, I know it's a little hard to see, I apologize. At this bottom left, maybe I could zoom in, but we can see that we have our full data, our 8 bytes turned on right now because these are all on. So if I start turning them off one by one, then we can see, or 2 by 2, my fingers are a little too big, so they're all turning off. There isn't, oh, this guy's just kind of stuck. And then we have over here on the right, our address. So what we can do is, since our instruction pointer is at the value of 1 right now, over here on the right, and our IMARS is also at the value of 1, we can set maybe from address, let's say 1 to 10 or something like that. We could just set some values that are going to be easy to remember, just to test to make sure that we can program the RAM, disconnect from it, and then have the instruction pointer itself and the IMAR talk to the RAM and get the quasi instructions out. So let's give that a shot. So we're at value 1 right now, the address 1. So I'm going to turn on only the 1 bit here of our address, and let's just turn on the most significant bit to make it kind of easy. So our first light here should turn on. So it does. So what I'm going to do is I'm going to hit this button connected to the white cable, which is the right button for the RAM. So click that, and that should have written there. So if we do a test, if we output the address from our controller and we hit read, then we do have a 1 there. And if we reset our bit, let's make sure it still works. And it does still read that 1. So that seemed to have worked there. So let's move up to memory address 2, which is 10 in binary, right here on our address input. And let's turn on now the 2 most significant bits. So let's do a preview. Our 2 most significant bits are on. Let's output this address, output the data we want, and write to it. So that should be there. Let's check to make sure it's reading, and it is. Now let's go to memory address 3, that's 11 in binary. And let's also turn on the 3rd most significant bit. So we just have a nice 3 lights on, make it easy to remember. Let's output the address and write. We can do a check to make sure it saved, and it seemed to. Let's move up now to address 4, which is 100 in binary. And let's turn on the 4th LED. And there we have the first 4 LEDs on. Output the address, write to memory, and it did write. And now 5101, 5 LEDs on the most significant bit side. Let's go to 6 now, which is 110 in binary. 4-bit turned on, 2-bit turned on. To top 6 bits, there's our test. Output, write. Let's do 7, 111 in binary. Output, looks good. Write. 8, 1000. Turn on the 8th bit. Looks good. And write. So now if I reset our address here and basically disconnect from the system, right? Leaving the RAM on, but disconnecting here our data input and our address input, right? So our programming is done. We can just imagine if we just wrote some programs into the RAM. And then what we want to do is we want to see if as we connect now the IMAR, right, which is connected through these black cables, but these 245s are turned off. So it's almost like these cables have been plugged out. This is disconnected. Even though it's plugged in and plugged into the RAM, it's in a disconnected state right now. We need to turn it on, and then we can start sending this data to the RAM, because if we press read right now, it's going to be garbage data because there really is nothing driving the RAM address lines. It's completely floating. Nobody is connected to it, even though we have these wires plugged in. So we need to enable our output with those 245s, and we'll just do that by manually grounding the output enable. In the future, this is going to be automatic, of course, but for now, it's just going to be manually done. So right now, we have now enabled, we've opened the gates, we've enabled the IMAR to go into the RAM. So the RAM is now, should be getting the address 1. And since we programmed that first significant bit to light up, that's what we should expect to see. So if we hold down our read, we can see that now it's accessing this memory address, going from the IMAR, right? From the instruction pointer to the IMAR, saving this value, then outputting through these cables, basically asks the RAM, he's going to say, hey, we're supposed to be executing memory position 1. What's the instruction there? And the RAM is going to output that the instruction is 80 in hex, right? 10000000. And then ideally what we'd have after this is an instruction register that this is then passed to, and then we can decode it. But for now, this is just loading the instructions. We could say this is the memory address pointer, which is probably a better name than memory address register. And then this is actually that value dereferenced, right? So it's kind of like we're dereferencing this pointer and getting this byte value. So now let's increment our instruction pointer, which will populate the IMAR or the IMAP, if we're going to call it a pointer. And then we'll see if the RAM is able to pick up those instructions or the temporary placeholder instructions. So let's increment. We see our instruction pointer went up to the value of 2, and it's going to now send it over to the IMAR. So we have value 2 now. And if we look at our RAM, then we see that our 2 lights are on, which is exactly what we had at address 2. And if we continue to increment, instruction pointer is now at 3, IMAR is now at 3, and our memory address has looked up the value that we put at 3, which is the most significant bit, the top 3 turned on. So we can continue to cycle through, and we'll see that all of the data that we put there is coming back out. So this looks really good for what we need. We're able to now have somewhat of an automated system where we can actually program the RAM and then have what we wrote loaded in sequence. So it's sort of incredible that just with these few components, we're able to have some sort of automated system. So if we just decoded this value here, then we can have a very, very basic CPU that is actually executing code, which is really, really crazy to think. Now, in this case, we're not going to decode from the memory output itself. We're going to copy this to an instruction register so that it's nice and stable. And the RAM might be doing all sorts of stuff in between these CPU cycles, depending on how advanced the CPU gets. So we want to, as soon as we can, just grab this data, move it somewhere safe, and let the RAM continue to work on anything else that it may be doing to sort of not clog up the system. So that's what I'll be adding next, hopefully, is an instruction register that will copy this actual data. Everything else so far has been an address. This is an address, this is an address, or we could say these are pointers. The RAM itself, of course, deals with addresses. This is an address. So this is actually the first byte, the first 8 bits of data itself that we have written that is going to be able to be accessible. And then we can transfer this to our instruction register and then decode it to have all sorts of cool stuff happen. In the beginning, we'll just turn on some different colored lights, I guess, with different instructions. A couple caveats. Right now, I have to manually, like I said, I have to manually turn on the IMAR to talk to the RAM with this blue cable. And I have to manually pulse the output enable on the RAM. But this is all very minor stuff that will be automatic very soon. But right now it's really good for testing, just to make sure I don't have any mistakes. I like having to proactively connect some of these things just to make sure I don't short or fry something out. So I think this looks great. And if we continue to go upwards, we'll just start seeing garbage in the RAM because we didn't program any of this stuff. So we'll see what happens when we have floating data, floating inputs, and just garbage data that went into our RAM. This is something where we'll have something like mem set, where we're able to set the memory and just kind of zero everything out in the beginning if that's what we choose to do. But kind of cool to see all this random data that's in there. I think it's really good progress. Thanks again, Regia, for suggesting that I clean this up. I started with these cables here, which are still kind of messy, an improvement, but still messy. And then I did these and these, and I felt like I was getting a little better. And then this was relatively clean. And to me, this is probably the cleanest that I've gotten so far, these black cables on here. I don't think my camera's focusing. Still a lot of room for growth when it comes to neatness and cutting these cables properly. I did, by the way, use 28 gauge wires here for these connections, which I sort of regret because they do get a little bit loose. So I might need to swap these for the 22 gauge, which are a bit thicker, like these orange cables right here. But next up, I will be trying to get our instruction register going where we can transfer the output byte, save it, and then we can start to get some basic decoding going on and hopefully get some minimal execution happening on our 16-bit computer. So thanks very much for joining me. This has been really fun, really eye-opening, and really fascinating for me. Thanks one more time to Regia for holding my feet to the fire when it comes to maintenance, because it's hard sometimes to stop and think about making something more organized when you're trying to just continually add features. So a really big help there. And by the way, these green cables, I didn't turn these into like semi-permanent cables yet because I think this CPU clock and state machine is going to bounce around a little bit. So I'm keeping these long cables just so that they can work no matter where I move this to. But ultimately, they will be much neater cables that carry these clock signals, which I'm trying to keep everything clock related to green. You can see the clock synchronized here in green and synchronized here in green and synchronized here in green. So green is my clock color, I guess you could say, clock signal. But yeah, so I'll catch you soon. Thanks very much for watching, and let's keep it rolling.